This is the last part of tutorial 3 on combustion. In the last two parts, we have discussed about the calculations related to GCV and NCV, and then we have seen how to calculate the minimum theoretical air and the various gas composition. In this part, we will first discuss about the 3 T's of combustion and their significance on combustion. See, this is important for BOE definitely, but it is also important for regular boiler operation. If you are a boiler operation engineer, this is the most important thing to understand. So we will first discuss the 3 T's of combustion, and finally we will discuss about the combustion optimization, right? So let us start with the 3 T's of combustion. If you have studied in mechanical or electrical engineering discipline, then in the second year you have studied the thermal engineering, and you know what 3 T's of combustion is. It is time, temperature and turbulence. Now almost universally it is spoken in this particular sequence: time, temperature, turbulence. Now we will first look at each individual T and understand what they are and what are the significance of this T in combustion conditions. So let us start with time. There are basically 2 times here. One is the reaction time, the other is the retention time. So if I talk about reaction time, the reaction time is the time required for complete combustion of a fuel particle. So naturally it would depend on few things. One is the type of fuel and the fuel characteristics also. So if I talk about the type of fuel, you see, gaseous fuel would take less time as compared to liquid fuel, and liquid fuel would take lesser time as compared to a solid fuel. So that is one thing which will depend on the type of fuel. Now if I talk about the fuel characteristics, then we have discussed that the solid fuel, which is having more volatile matter, would require less time for combustion, right? Because high volatile fuels are reactive fuels and it requires less time for combustion. So that will depend on the fuel characteristics. The other thing, apart from the type of fuel and fuel characteristics, particularly in case of solid and liquid fuel, is the particle size. See, a larger particle size of fuel would naturally take more time for combustion as compared to a smaller particle size of fuel in case of solid as well as liquid. So in liquid fuel, say, if the atomization is not proper, so large particle size of the liquid fuel would take more time to burn, right? That's why the flame size, the flame length may increase in case of improper atomization. Now if I take a look at this time in case of a pulverized coal-fired boiler, so in a pulverized coal-fired boiler, usually the coal particle size which comes to the furnace is, we have discussed that it is about 70% should pass to 200 mesh size. In terms of micron size, it is usually around 30 to 70 micron size particle that comes in the furnace. Now the furnace is having high temperature, so the instant it comes inside the furnace, the first thing what happened is the volatile matter and the moisture, it goes out of the fuel. So that is called devolatilization. What remains is, after the volatile matter and the moisture removes, what remains is char, right? Now there would be 2 combustion mechanism here. One would be the volatile combustion, which is going to be a homogeneous combustion mixture, because volatile is gas, it is going to create a homogeneous mixture with air. And there will be a char combustion, which will be a heterogeneous combustion mixture, right? So if I talk about the total time T, now the volatile removal of volatile, that is the devolatilization, is going to take very little time. within 1 to 5 milliseconds the devaluation will take place. Then the volatile combustion will take around 50 to 100 millisecond time, so it's faster. But if I talk about the total combustion of the char in a standard pulverized coal-fired furnace, it takes usually 1 to 2 seconds, right? So that is the reaction time we are talking about. If I talk about the retention time means how long the particle stays in the combustion zone, right? That is the retention time. Now, how long it stays in the combustion zone will depend again on first the velocity of the flue gas and the velocity of the particle. Higher the velocity, lesser will be the retention time. And again, the velocity of the flue gas is not the only component which is going to influence the velocity of the particle. It will be also the particle size in case of solid and liquid fuel. So that's about the time. If I talk about the temperature, that is a simple one. It is the ignition temperature. Ignition temperature is the temperature at which the fuel ignites and the combustion is retained. That is, it continues the combustion reaction. Now, this temperature, ignition temperature, if I take a look at the various combustible ignition temperature in a solid fuel, then you see the fixed carbon, that is the carbon part, would have a ignition temperature of around 400 degrees centigrade. In fact, this is the reason why in a coal-fired boiler, unless the furnace temperature is in the range of 550 above, we do not introduce coal, right? Because to ensure the char combustion, or rather the fixed carbon combustion. All the hydrocarbons, which are the volatile matters basically, are in the range of around 500 to 650 degrees centigrade, right? In fact, you would note that the CO combustion ignition temperature is the highest here. That means once carbon becomes CO, it would still not react with oxygen unless it meets the oxygen or comes in contact with the oxygen where the temperature region is above 655. Okay, so this is the ignition temperature of various combustible. Now, talking about turbulence. So what is turbulence? Turbulence is basically the mixing of coal and air to create the contact with oxygen with the combustible in the fuel, right? In fact, you can understand that unless there is a contact with the oxygen with the combustion is not going to start actually. The combustion would start only when the combustible comes in contact with oxygen and there is ignition temperature available, then it is going to start. And then the question of time comes, how long it's going to take for complete combustion, and how long during that period, how long it's going to stay in the desired combustion zone, right? So that means if I talk about the time temperature turbulence, the sequence of this T should be actually turbulence first, ensure the contact, then the temperature, then the time. You'd understand the significance of this more if I take a look at the furnace temperature profile, right? So first we take a look at the gas temperature profile of in this case, a pulverized coal-fired furnace. Now, in the furnace region, the temperature usually remains in the region of 11 to 1200 degrees centigrade. Near the platen superator inlet, the temperature comes to around 900-950 degree. Near the final superator inlet, it comes to around 800-850 degree. When it passes the final superator, that is called the furnace exit temperature, that is usually in the region of less than 700 degrees centigrade. The eco inlet temperature is in the range of 450 to 480 degrees centigrade. The APH inlet temperature is in the range of 350 to 380 degrees centigrade. And the stack temperature is in the range of 130-140 degrees. This is a standard temperature profile for not only the pulverized coal-fired boiler, you can see in a oil and gas-fired boiler also it remains in this region only. That means if I consider a condition where the carbon finally meets with the oxygen, let us say here, in this area the temperature is less than 400 degrees centigrade. Therefore, the carbon is not going to take part in combustion. There will be no combustion of this carbon. As a result, what is going to happen? Both the carbon particle and the oxygen particle will go out of the furnace as it is. That means we will have a higher oxygen level in the APH inlet where we measure the oxygen. We will also have the unburnt carbon particle collected in the ESP hoppers, right? If you consider that this carbon and oxygen is meeting somewhere here. Now this is a location where the temperature is there, 650, 700 degrees centigrade temperature. Therefore, the combustion is going to take place. The question is, do we want it? Answer is no. This is called secondary combustion. This is not only undesirable, it is highly unsafe basically. It is not going to give us any benefit of this combustion. Only the odd temperatures will go up, which we do not want. Consider a case where the carbon and oxygen is meeting at the inlet of the platinum superator, right, near the platinum superator. Naturally, the temperature is very high, so there will be combustion. Again, the question is, do we want it? Answer is no. This is called delayed combustion, and this in fact is the most common problem with the majority of the boilers, right? It confuses people. Again, it doesn't help us in any way. It would increase the temperature of the superator and reheaters. It is going to increase the temperature spray, right? And it is not going to help us in any way so far as the steam generation is concerned. Now take a look at the furnace area where the temperature is in the range of around 900-950 degrees centigrade. Now, do you see any place where this volatile matters, that is the hydrocarbons, if they come there, it will not have the combustion? Apparently, there is no such place here. The temperature is very high. But if you take a look at the metal temperature, let us say the water walls. These water walls are made of carbon steel. And carbon steel has got a temperature limit, and that is 370 degrees centigrade. If the carbon steel temperature is allowed to go above this, there is a phenomena called creep that is going to come into carbon steel, and carbon steel does not have any kind of resistance against creep. Therefore, the temperature of this water wall metal, in case of subcritical boilers, naturally, has to be less than 370 degrees, right? This is ensured by ensuring proper circulation in this evaporator section. Also, if you see the superator metal temperatures, the final superator will be in the range of, steam temperature will be in the range of 540-550 degrees centigrade max. Whereas the platinum superator will be in the range of 450-480 degrees centigrade. Therefore, the metal temperatures are also very close to the steam temperature. So, in the range of around 450 to 550 degrees centigrade will be the metal temperature. We have seen the hydrocarbons are having some of them are having a ignition temperature of around 600-650, right? So, if they come to either the water walls, metal contacts, or the superator metal, they come in contact, it will become cold, right? There will be no combustion. What happened is, after a long time, there will be a degradation process called pyrolysis. These hydrocarbons will go out, and what will remain is a layer of carbon, which we know as soot deposition, soot formation. This soot formation is going to further restrict the heat transfer to the water walls and the superators. But the first thing we need to understand that whenever there is a soot formation, it is because of improper combustion. There are combustibles which were supposed to take part in combustion, which is not, right? So there is a combustion mistake. So all this consideration that the carbon particle cannot go here, it cannot go up, it cannot touches the wall, all these things tells us that the most important T in the 3T is the turbulence T. We need to ensure the contact of the combustibles with air at the right place. Have the combustion at the right location, then only we can have a combustion optimization, right? It is actually more important how you are giving the air rather than how much you are giving the air. How and where you are giving the air is much more important than how much. Most of the systems are running with high air, higher than required air. Why? Because we are not giving the air at the right location, right? It is not properly utilized. So when we talk about the total air, how it is given, we all know the air is coming to all the furnaces in two parts. One is the primary air, another is the secondary air. So first thing we need to understand, okay, what is the role of the primary air and what is the role of the secondary air? How much it should be given, how we are giving, how much we are giving, all these things have to be considered first. So let us say first the primary air. What is primary air? It is basically the air which is coming with the fuel, right? So the role of the primary air in combustion is to create a combustible mixture which will ignite and start combustion once the temperature is available, right? Now this combustible mixture should be an optimized air-fuel mixture. Neither do we want high amount of air which will make it a air-rich mixture, nor do we want a low amount of air which will make it a air-lean mixture or fuel-rich mixture, right? In fact, if you see that if you are using high amount of primary air, right, one thing it is going to do, if you are using too high, it can actually create a flame failure condition for a very high air-rich mixture condition. If at all not that happens, then one thing is definitely going to happen. If you are using more primary air, it is going to reduce the secondary air. Why? Because the total air we are controlling, because we are controlling the air by O2 measurement. The excess air is controlled by excess O2 which we measure at the APH inlet. So if you are using primary air higher proportion, that is going to definitely reduce the secondary air, right? Another thing is that oxygen rich condition in the initial stage of the combustion is going to increase the possibility of the NOx formation as well as the SO3 formation, right? Because that is the high temperature condition and NOx is a high temperature reaction. SO3 also would be a possibility here because SO2 becomes SO3 when it reacts with nascent oxygen, and nascent oxygen is usually available in the preliminary condition of the combustion where the temperature is very high. The role of the secondary air, on the other hand, is what? This air is going to ensure the complete combustion. Once the combustion starts with the primary air, the role of the secondary air is to ensure the complete combustion. Another very important role of the secondary air is this particular air is actually contributing to the turbulence, right? High delta P across the furnace to wind box, which is always measured in all the boilers, this is the parameter which actually contributes to the turbulence in the system, right? So that is the role of the primary air and secondary air in combustion. But there are some other roles also, right? Now if I talk about the additional role of primary air in case of a pulverized coal-fired boiler, what is that? We know that primary air in a pulverized coal-fired boiler is given to the mill, right? So one job of the primary air is to lift the coal air mixture to the furnace, right? Naturally, that means that if I need more fuel, I would need more primary air. So the primary air in this case would be proportional to the coal mass, right? It is not exactly related to the combustible. We know the air is required for the combustibles, but in case of a pulverized coal-fired boiler, the primary air would be proportional to the mass of coal fuel that is to be uh, given to the furnace. So naturally, if I am having a low CV coal, right, uh, that is going to increase the PA proportion, because in case of a low CV coal for a particular heat load, I would require to put more amount of fuel in the furnace, and that would require more amount of primary air, which is going to take this fuel to the furnace. Reduction of primary air. If I want to reduce primary air, then the first thing it is going to do in a pulverized coal-fired boiler is it is going to increase the mid reject, or the unburned in the mid reject, right? That is the first thing that is going to happen. In the worst case, if I go on reducing the primary air, it may affect the furnace temperature, because the coal would not be reaching the furnace, the pressure, and the steam load, that is the steam pressure, because the steam formation would not be there because fuel is not going inside the furnace. And in the worst case, it can also create a fuel pipe choking, right? It will start with reduction of furnace temperature and steam pressure, and in the worst case, it may lead to the fuel pipe choking. If I consider the role of the primary air in case of fluidized bed boiler, ABC boiler, ABC and CFBC, then in a BC boiler, the primary air is actually we are using for the fluidizing air, right? We give it from the bottom through the air nozzles. So this is the job of the primary air in case of fluidized bed boiler. Naturally, if I reduce the primary air, what is going to happen? The fluidization will be less, therefore the bed temperature is going to increase. Now we know that is the most critical parameter in case of a fluidized bed boiler, right? So that creates a limitation to us in order to reduce the primary air. This particular thing, if I talk about the reverse case, if I increase the primary air, which I usually do to control the bed temperature, it is going to lead to high amount of unburned in the fly ash, particularly with smaller particle size. There will be a lot of unburned in the fly ash because we are having higher velocity, fuel velocity, and because of the higher velocity, it is definitely going to increase the erosion, right? This particular problem will be magnified if we do not maintain the nozzles. See, if you see a nozzle is choked, what is going to happen in that particular region? The fluidizing air will be less, right? That is going to increase the furnace temperature, bed temperature. But the same amount of air will be going through the other nozzles. There the velocity will be higher, and that is going to lead to more unburnt, right? So maintaining the nozzle health is a very, very important thing in case of a fluidized bed boiler. Now, talking about the combustion optimization, let us now come to this. We need to understand that combustion optimization approach has got two distinct parts. The first part is optimizing the combustion condition, right? Now, this combustion condition is optimized by optimizing the 3Ts. After doing that, then we think about optimizing the combustion air, that is the excess air control. The normal understanding is when you say combustion optimization usually is optimizing air, but we need to understand that before optimizing air, we need to ensure that whatever air we are giving is properly utilized, and that can only happen if we can optimize the 3Ts in the system, right? So combustion condition optimization, that is the optimization of the 3Ts. The approach would be twofold. One is optimizing the SA2-PA ratio, increasing the turbulence, reducing the PA, increasing the SA, increasing the turbulence that way. And the second thing is optimizing the particle size also, right? So these are the two approaches in optimizing optimizing the 3D condition. We also need to ensure that the combustion is taking place at the right place. In case of a corner fired boiler, it should be centrally located. It should not go too near to the platinum superheaters, right? The furnace superheaters and the heaters. Those are the things we need to ensure. Why we need to ensure optimized air? Because if I talk about the negative aspects of excess air, high amount of excess air, the first major problem when we are using high amount of excess air is the high dry gas loss, sensible heat loss through the dry gas. We are using the air at ambient temperature. When it is going through the stack, it is going with a high flue gas temperature. So a lot of heat is going out of the system that way, which is sensible air. If I am using more air, there will be more dry gas mass and the total loss is going to increase, right? So that is the main thing. Again, when you are using more than required air, that means we are using the PA more, FD more, right? And in case of a balanced draft furnace, the ID has to evacuate more gas. So both the FD and ID fan auxiliary power is going to increase in case of high excess air. The third problem is the formation. We have discussed that particularly in case of a high primary air, there will be more chance of NOx formation as well as SO3 formation. Then since the air is more, the velocity would be more, and if the velocity is more, the erosion, which is a very very dangerous or rather most problematic thing in case of a solid fuel fired boiler, that is going to increase manifold. Actually, the relation between erosion and velocity is like erosion is going to increase as the fifth power of the velocity. So if velocity increases, erosion is going to increase proportional to the fifth power of the velocity. Another problem of using high amount of excess air is that in case of a balanced draft furnace, more the mass of flue gas, more would be the power required for the ID. And this way, if the ID power reaches the limit, that we call it saturation of ID, what is going to happen? If you need to increase the load further, you need to put more fuel, which will not be possible in this case because the more amount of flue gas inside the furnace is going to start increasing the furnace pressure. And in the balanced draft system, the furnace pressure is maintained by the ID. Now once the ID is saturated, you cannot allow the furnace pressure to go up, therefore you cannot allow the fuel load to go up. So that it creates a limitation on the boiler load. And finally, when we are using more air, that means we are reducing the furnace temperature. And if you are reducing the furnace temperature, we know that the radiation heat transfer which is taking place in the furnace area is proportional to the fourth power of the temperature of the flue gas, right? So therefore, the radiation heat transfer is going to get reduced. Now this heat load which is not getting transferred in the furnace area will go to the second pass. And with more amount of air, the flue gas mass would be also more, so the mass velocity will be more. So the second pass heat transfer is going to increase, right? But we have also seen in heat transfer that radiation heat transfer is a much superior mode of heat transfer. Any heat transfer which is not done in the radiation zone, that cannot be taken care of by the convection zone, right? So there will be some amount of heat loss. In short, the exit temperature is going to increase. So let us now take a look at the combustion optimization steps in case of a pulverized fuel fired boiler first. In fact, we will discuss the optimization steps with reference to pulverized fuel fired boiler, because simply it gives in terms of BOE, it gives us more point to write with, right? So we need to check few parameters first. The ultimate analysis of the coal, the O2, CO, CO2. Now see, the ultimate analysis of the coal is to be measured for the measurement of theoretical air. The O2, CO and CO2, this we will see in case of performance calculation. These three would be required to measure the CO loss, the incomplete combustion loss. The unburned in the fly ash and the bottom ash to understand or rather to optimize the fuel size. The platinum separator inlet temperature, that is to understand where the combustion is taking place, whether delayed combustion is there or not, and the boiler exit temperature, right? Stack temperature, that is for the also for the measurement of the dry gas mass loss, sensible heat loss to dry gas. The furnace wind box DP to understand the turbulence. The PA and FD mass flow is measured to measure the total air. The fuel flow to measure the air to fuel ratio, and the mill reject also we need to measure when we are reducing the primary air. If the mill reject is increasing, we simply measure it and see which loss is more, the mill reject loss is more or the combustion loss is more, right? These are the few parameters we need to measure in case of combustion optimization process. Now if I take a look at the steps, the combustion optimization step would start with the measurement of the theoretical air, minimum theoretical air for complete combustion, which you can do from the ultimate analysis. This we have already done in the combustion calculations. The next thing you do is to calculate the total air, right? The PAFD flow you calculate the total air. Then you calculate the fuel flow, and finally you get the air to fuel ratio. This you remember is the actual air which we measure, air to fuel ratio, the total air. Now if you know the total air, if you know the theoretical air, minimum theoretical air, you can also calculate the excess air, actual excess air that is being going there. Now our optimization process will start with optimizing the 3T's condition, right? So as I told you, the first approach is we want to have an optimum SA to PA ratio. So what we do, we start reducing the PA, but it has to be done by small margin, not just reduce it with a large amount, just reduce it by small margin. Now the moment you reduce the PA, two things would happen. As I told you, first is the mill reject is going to increase. So what we do, we check the mill reject, and then we also check whether it is leading to the fuel pipe choking, right? This is not going to happen suddenly. Suddenly the fuel pipe is not going to choke like that. What is going to happen? It is going to start reducing the fuel flow to the furnace first, and that is going to result into the reduction in the furnace temperature and pressure as well as the steam pressure. So we keep a monitor on the furnace temperature and the boiler pressure. The moment it happens, we stop reducing the PA, right? So these are the parameters we monitor, and we start reducing PA. But the point is, we are not optimizing the air here, we are optimizing the condition. So what we do, whatever PA we have reduced, we increase the SA by the same margin, right? And the furnace DP, furnace to wind box DP is going to increase by that. So we are targeting increase of turbulence. Now whenever we are changing the PA, this is the time to also have the proper fuel particle size, right? So what we do, this is the time when we set the classifier accordingly to change the fines, right? What is the idea? Idea is to have the optimum unburned in the fly ash and the bottom ash, because we are changing the velocity, so we also have to change the fuel particle size. So by adjusting this, what we do, we are optimizing the 3T's condition, and this will continue. We continue reducing the primary air and secondary air. In a pulverized coal-fired boiler, corner-fired boiler, we can also change the burner tilt to have the proper combustion location. So the temperature of the platen super inlet will be minimum at that time, or rather the desired temperature would be attained. So we change the burner angle, the tilt angle accordingly. and we continue reducing the PA, increase the ASA till we reach the optimum. Sorry. Now when we would understand that we have reached optimum condition, see, we are not changing the total air. Now if I am changing the condition and my O2 is reduced, what does it indicate? It indicates I am utilizing the air more, because O2 which we measured at APH inlet is the unused O2 basically, which is going to the APH inlet, right? So this is the time when we measure the O2 and see it is minimum. We also measure the unburned and see it is minimum. Then we understand, okay, we have reached a condition where the combustion 3Ts are optimized in the furnace. Now this is the time when we go for the optimization of the air. Now when we are measuring the excess air, excess O2 in a balanced draft system, the furnace and the rest of the part, the combustion, the convection zone and all the part, these are all under negative pressure. Any leakages is going to bring air ingress to the system, which is going to create a faulty measurement of the O2. So the first thing we need to do is we need to identify the leakages in the furnace and we stop furnace ingress as much as possible, right? Once it is done, now we calculate two losses. One is the incomplete combustion loss, that is the CO loss. I am going to show you how to measure the CO loss when I discuss about the performance. And we also measure the sensible heat loss through dry gas, right? And we create a curve for these two losses to see where the optimized condition is located, right? And we select an optimum air zone. Now I'll show you how it can be done. If I create a graph against two losses, one is the two part components. One is the amount of air in the x-axis and amount of loss in the y-axis. Now if I consider the CO loss, the CO loss will be minimum when the air is minimum, and as I increase I would rather say the CO loss will be maximum when the air is minimum, and as I increase the air, the CO loss will go down. So the CO loss curve will be something like this. The dry gas loss on the other hand will be minimum when the air is minimum, and it is going to increase when the air is increased. So the dry gas loss curve will be something like this. If I want to have zero CO, okay, let us say here, the resultant dry gas loss is going to be very high. Therefore, when I say that I cannot have zero CO, I should have some amount of CO in the flue gas, right? That means we need to select an air zone in this area, which we should say the optimum zone. And once we have selected it, whatever the O2 measurement at this point will be the desired O2 for us, right? So this is how the combustion optimization would be done. With this, I conclude the combustion chapter. In the second part of, or rather the next part of the tutorial, I'll be dealing with the draft calculations, the calculations related to natural draft and the fan draft also, the fan powers, the ID fan power, FD fan power, all those things we'll deal with in the next tutorial. Okay, till then, thank you very much. Goodbye.